Hi everyone, welcome to lecture. 24th lecture of 188. Before last one, let's take a look at what's left. So we have the final contest, which is due tonight. In the final contest, you get to design an agent that plays together with another agent to try to collect food pellets while not getting eaten by ghosts. And there's a few staff agents to compete with, as well as a leaderboard against other students. So submissions for that, your last chance to submit are tonight at midnight. And on Thursday in lecture, we'll discuss the results. What else is left? There is there is a project due next week. There's still a section this week, and I think the homework is all wrapped up, but you would still have a self-assessment of your last homework that will be due next week. And then there's a final exam the week after that. Any questions about logistics? Yes?
Will it be graded on the last activated font or all fonts of the final contest?
You will be graded only on your last submission. So yeah, don't ruin it in your last submission. Any other questions? Okay, let's dive into technical materials for today. So today's lecture, as well as Thursday's lecture, will be mostly on advanced applications. The idea behind these two lectures is to look at advanced applications where we have covered a good amount of the material and the ideas behind those applications, but not necessarily everything, but enough to get an idea of how these systems might work. We will not quiz you on these application lectures on the final exam or anything like that. It's more meant to give you more perspective rather than extra study materials for the final. So far we've looked at foundational methods for search, for acting in adversarial environments, for learning to do new things, and for dealing with uncertainty, noisy information. We've seen it all in the context of Pac-Man trying to solve a wide range of problems. Let's take a look at some counterparts in real-world applications. So search is very prevalent in language processing, and we'll cover some of that on Thursday. Adversarial games, we'll look a bit more at AlphaGo, arguably the most prominent result in gameplay in the past few years. Learning to acquire behaviors, we'll look at some real robot behaviors in flight and in legged locomotion. And dealing with uncertainty, we'll look a bit at the current state of self-driving cars. So, AlphaGo. Today's state of the art in Go is that there are computer players better than the best human players. But actually, if you went back to March 2016, that was not the case yet. In fact, this is a headline from first week of March 2016, a little over 2 years ago. Google is trying to make artificial intelligence history, and it could happen this week. This was alluding to the match AlphaGo was going to play against Lee Sedol later that week. What happened is AlphaGo actually won the majority of those matches and in some sense became new world champion. And in 188, we had to update this graph that you see at the very beginning of the course where we had already checkers fully solved, which means we understand who can guarantee a win. Chess, computers play at beyond human level, and Go, now also the case. So, how do you make an AI for Go? Let's go back to what we were looking at in lecture on games. Minimax. Minimax is about solving games in adversarial environments. You have your own player, but then there's the opponent plays against you, and you reason about what you will do, what they can do, what you can do, all possible ways the game can play out. For a game like tic-tac-toe, you will find out that you can force a draw, and that means fully solving the game. But for a game like Go, that's actually pretty hard to do, and it's even much harder than chess. And why? Let's take a look at chess. This is an animation made by DeepMind showcasing the branching factor in chess. It's large. It's much bigger than tic-tac-toe. You're not going to easily compute all possible scenarios in chess. Hasn't been done yet. But it's still somewhat reasonable. For Go, here's what it looks like. The branching factor is much larger. It's a 19 by 19 board, so there's 19 times 19 positions to choose from in the first move, and then one less, of course, next move, but the branching factor is enormous. And so if you try to run exhaustive search through this kind of game tree, it's not going to work. We also saw that alpha-beta pruning in the ideal expansion scenario can reduce the size of the tree by square rooting it, effectively making it half as deep. Still too much. You can't work through this even if you had the perfect ordering in alpha-beta pruning. So what else can we do? What we saw is that maybe you can decide not to search as deeply by having an evaluation function. Now, evaluation functions can be difficult to design, and what was so special about AlphaGo is that the evaluation function was learned. A deep neural network was trained to provide a good evaluation function at various stages of the game. And so when you think about your move, maybe you only have to think too deep instead of all the way till the end of the game, because after too deep, you look at the evaluation function and it might be good enough. We know neural networks are universal function approximators, so in principle they could represent the exact evaluation function. Of course, that would require a lot of data, and in fact data of optimal players, which we don't have. But maybe if you have enough data from pretty good players, you can train a neural network to evaluate the value of a position, let's say scored between 0 and 1, according to a win probability of white, let's say. But even then, because the branching factor is so large, the evaluation function, sure, if you want to look one step ahead, no problem. But if you want to look a little more than one step ahead, the large branching factor is still a bit of an issue. But many of the moves are not that useful. And so question you can ask, can we learn another neural network that can tell us how to reduce which moves to consider when we do our depth-limited search? And so a policy network can be trained, which assigns probabilities to all possible moves, and then you might only consider the moves with high probability when running your search, or you might just sample from that distribution to run your search. So it learned two networks, a value network, which learns the evaluation function, and a policy network which reduces the branching factor. So let's look at the whole pipeline. For AlphaGo, there was a bunch of data collected from human play. Then a supervised learning was run. So a deep neural network was trained to predict who will win from a certain situation. So we've seen examples of predicting what digit. This would now be predicting who wins when this game is over. Then, this gives you, there's two things being learned from that. The first thing being learned is the policy network, which is deciding which move somebody makes. Once you have that, you can use that policy network to play against yourself, and you can keep improving your policy from playing against yourself. This gives you a lot of data. That lot of data can then be used to decide who is likely to win from a given situation, which is the value network. That value network, also a big neural network, can then be used with your look ahead. And so when you're testing, that is, you're actually playing with these networks, you will sample from your policy network, likely branches you might go down and your opponent might go down, and then you'll cut it off at a certain depth, use the value network there to propagate values up. One little additional thing that is pretty interesting about Go, and what a lot of the previous Go systems build upon pretty heavily, and AlphaGo builds upon too for supervision, is that Monte Carlo rollouts end up being reasonably good at predicting who's going to win. What do I mean with that? Let's say you're in a given board situation, and from that situation you just randomly play. If you do random play, it is likely that whoever's in the better position to win will also win in the random play. It's not guaranteed, of course, but they'll typically have a higher win probability. So that means you can self-supervise with pretty poor play. In fact, you can self-supervise with random play to learn who is likely to win from a given situation. These things combined led to mastery of the game of Go with deep neural networks and tree search combined. So bringing together two topics we've covered in this class. A year later, just about 1 year ago, another paper came out of DeepMind. This is October 2017, Mastering the Game of Go Without Human Knowledge. This one's called AlphaGo 0. And what they did there is they skipped the training on human play. So when we go back to the training pipeline, instead of training on human expert positions, from the beginning, it was just playing itself. And since we know that random rollouts tend to favor who is in a better position from the beginning, you already get some signal about what the right or wrong moves might be, even if your policy is still pretty poor. And then you can do this whole process from scratch without any human input in terms of what are good or bad positions. And in fact, AlphaGo 0 was then generalized to Alpha 0, which was used to also learn to play chess and, I believe, shogi, or some other board game that's strategic, similar to chess, but a little more complicated. So, what this shows is that the combination of what we covered at the very beginning, in terms of minimax, alpha-beta pruning, and so forth, with deep neural networks to help guide the sampling process through the tree and to guide what the valuations are when you cut off the search, can get you really good performance in games. Any questions about this? We'll cover a sequence of different applications one after the other, and this is the part for Go. Question? Yes? So, good question. What happens when there is no human input? It's trained by just playing against itself. And so, when you play against yourself, initially you're playing pretty poorly, of course, because you don't know how to play yet. It's a random neural network, or a network that's randomly initialized, making decisions. But what happens is that half the time you win, half the time you lose. And so it turns out that in terms of reinforcement learning problems you can phrase as you play against a version of yourself, and that kind of problem is much easier to learn than most other things, because half the time you win, half the time you lose. That's maximizing the amount of signal you get from data you collect.
So you mean you don't get as good as having human knowledge?
Oh, the final level achieved is beyond human level, way beyond. So there's some ELO scales where they look at for Go, and AlphaGo 0, which learns from just playing itself, goes at a level beyond where AlphaGo was. Strongest player in existence so far. And the longer it keeps playing itself, the better it keeps getting. There are often a few tricks you need to take into account when you do this self-play kind of thing, which is you don't want to just play exactly yourself necessarily, because you might overfit to your exact current way of playing. So usually you might keep around some past versions of yourself and play against an ensemble, like a set of past players, and make sure you're good against all of them, rather than just good against whatever your current strategy is.
If you have the same amount of self-training, which one do you think is going to be better? With or without human?
So, in some sense, the human knowledge put into it is looking at past games of humans and training a value network and a policy network to predict what happened in there. That gives you a better initialization of the neural network than random initialization. And so the question you're asking effectively is, okay, is it possible that that better initialization maybe steers you in the wrong direction, and maybe you're going to get stuck in a local optimum that is a lot like humans, but maybe if you learn from scratch, you can find something even way better? I don't know the answer to that. But empirically, it seems that learning from scratch reaches levels beyond the levels reached with the previous methods. But yeah, who knows? There's no final answer yet.
Is there any way of knowing if the approach without human knowledge will converge to like an optimal strategy, or could it be a local optimum and then another approach could be even better?
So there is something called fictitious play. In fictitious play, you kind of play against yourself in a slightly more complicated setting than this. So I believe it includes this. The result, if you by playing yourself, you're guaranteed to reach an equilibrium. But it's a kind of subtle way of reaching an equilibrium. What reaches the equilibrium is the averaged version of all your past selves. So rather than your actual current network being the equilibrium solution, it's the average of all past. Then there's something called neural fictitious play, which is where you train a neural network to match up with the average version of all your past selves, because that way you can do it more efficiently. Because if you need to keep around all your past selves, that's a lot to keep around, and that's not very convenient to use, especially if you need, let's say, thousands or millions of updates. But if you then train a network to match up with the average of your past selves, then you effectively get the same thing, and that will reach an equilibrium which tends to be local, doesn't need to be globally optimal. Yes?
Is there a point where the ego rating plateaus, and is there, I don't know, how long does that take for AlphaGo 0?
So AlphaGo 0, well, let me maybe see if I can pull this up easily, because I have a slide on that, just not in this deck, and then you can see it. It was still climbing, but let me see if I can pull something up that might showcase it. Okay, so here's AlphaGo 0. There's my cursor somewhere here. Yep. So AlphaGo 0 is compared with AlphaGo Lee, which is the version that played Lee Sedol, and then AlphaGo Master. So what happened is there was AlphaGo that played Lee Sedol, then there was AlphaGo Master, which was kind of released online play and was pretty much essentially beating everyone in somewhat faster games that are played online. And then there was AlphaGo 0, which is was more recent. So if we look at ELO rating on the vertical axis and then number of days of training on the horizontal axis, this is what happens. So AlphaGo 0 has no prior knowledge, so it starts with a negative ELO rating, loses all the time initially. I mean, it's playing itself, but then gets tested against a set of players to calibrate its ELO rating. And the green line is where AlphaGo Lee Sedol was. The blue dotted line, after 21 days, it goes past where AlphaGo Master was, which was an improved version of AlphaGo Lee Sedol, and then it was still creeping up after 40 days. Now, I think what you're asking is in some sense, at some point, if you keep going, you will be limited that you will, in some sense, solve the game. Like Go, even though it's a massive game, in principle has a solution. And so, in principle, you could, if you have training working out perfectly, reach a point where your neural network essentially knows from every situation who's guaranteed to win or whether it's guaranteed to be a draw, and then knows how to play that. I don't think this would be getting at that level yet. But at some point, you can reach that level. Once you reach that level, essentially there's no further to go because you solved the game. And I don't know what ELO rating would correspond to that. Any other questions about Go? Yes?
So do you think you can solve the game with enough computing power?
Well, it's a good question. So the question was, do we think we can solve the game with enough compute power? Now, with infinite compute power, for sure. That's a given. then you can definitely solve it. With reasonable compute power, to actually traverse the whole tree, even with alpha beta pruning, I don't think that'll happen anytime soon. It's a really big tree. I mean, it's essentially 19 times 19 times 19 is now times 19 minus 1 times 19 minus 2 and so forth, and that'll add up to a very large number. In fact, before deep learning became so successful, when people were speculating about how long it would take to get human-level performance on the game of Go, a lot of people were thinking in that direction, and were thinking, okay, how long will it take us before we can really traverse a very large part of that tree? And that's maybe when we reach human-level play. And when people made guesses based on that, they would say, well, maybe 100 years from now, maybe 50 years from now, maybe 20. But pretty much no one would say less than 20, and most people would say, 50 or more. If you do a more kind of brute force style approach. Not 100% brute force, it might be even longer. But the more brute force style approach where you don't have good value functions, you don't have good policy functions, was expected to take decades before we reach compute levels that can do that. Yes?
What are the advantages of not using human knowledge in this data that we have?
That's a good question. What are the advantages of not using the human knowledge? So one possible advantage ties into the earlier question. It could be that because you only find local optima when training neural networks, it could be that by using human knowledge, you're in some kind of basin of attraction for a local optimum that's maybe not as good as another one that might be out there. I don't know if that would be the case or not, but that's a possibility. It also depends on how much randomness you have in your exploration. So if you have enough randomness, then the initialization will have much less effect than if you have limited randomness in your exploration. Generally, if you want to solve a problem, usually you want to bring everything to bear you have. So you will bring to bear any data from humans, any human demonstrations you can get, and we'll see some examples in a few other problem settings soon, and then do reinforcement learning on top of that to further improve. That's kind of the standard way to solve a problem. From a research point of view, it's very interesting to see where you can get from scratch. So from a research point of view, it's a very clear question. Okay, what can we do if we don't have any prior knowledge? How good can this system get? Is it even possible to learn good Go players by just playing against yourself? That's something people did not have an answer to until this experiment was run. Okay, switching gears to helicopters. Here's a motivating example. Imagine you want your helicopter to do something like this. It's called a tick-tock, after how old school clocks would have something that swings back and forth. This is a very hard maneuver to do. Only extremely capable pilots can do this. I don't think they do it with helicopters you sit in. This is an RC helicopter. How would you get a helicopter to do this autonomously? And by the way, this is done autonomously here, but how do we get to something like this? Well, what does it mean to fly a helicopter? What are the challenges? There's two key challenges. One is tracking where the helicopter is at any given time, because if you don't know where it is, you're not going to be able to control it very reliably. That ties into things we saw with HMMs. And then the other thing is to decide what to do, what controls to send to the helicopter. So, what do you get to send to a helicopter? Typically, you have a remote control, which has two joysticks. You send controls from that to the helicopter. Then helicopter might listen to those, but you need to decide what to send. So you might have a computer that does some kind of calculation that feeds into the back of this remote control to send things out. Then the helicopter often on board has some sensing, maybe inertial measurements unit, which measures the acceleration of the helicopter. So it's a 3-axis measurement, X, Y, Z. How much is the helicopter accelerating relative to gravity? Free falling is measured as 0. Then usually there's a 3-axis gyroscope, which measures around 3 axes your angular rate of your helicopter, and often there's a magnetic compass which measures which way the helicopter is facing relative to the direction of the Earth magnetic field. So those are all measurements you get on board. Actually, you might have a GPS, but they might not be that reliable when you fly in such aggressive maneuvers, and they tend to be somewhat imprecise. So it's hard to stabilize a helicopter when you only know where you are up to a couple meters. It's much easier to have more precise measurements. So, for example, you might put cameras on the ground that can position the helicopter reliably. So, how do we track the helicopter? None of these measurements are super precise. So we set up a hidden Markov model where we consider the state unknown. The state is x, y, z, then the three angles, the velocity, and the angular rates. And the measurements are the measurements I just described. So by running inference over time through this HMM forward algorithm, we can at any given time know with some reasonable level of accuracy what the state is of this helicopter. We also need a transition model for that, which goes from S0 to S1. So there will be some function that says, given current state in action, what's the next state? But only up to some noise. It will not be perfect. So how about then solving the MDP itself? What are our controls? We have 4 control channels, 2 in each joystick. We have, let's start with the collective. That's A collective is the action for the main rotor collective pitch, is the average angle of attack as the blade goes through the air, which modulates how much vertical thrust you generate. There is cyclic controls, longitudinal and latitudinal cyclic controls, which determine the difference in angle front, back, and left, right as the blade goes around. So that way you can generate a torque that allows your helicopter to roll or pitch based on how much differential thrust you have front, back, left, right. Then the tail rotor has a variable pitch also, and that pitch allows you to modulate how much thrust you get from the tail rotor. So that's how you control a helicopter. You cannot directly ask it to fly forward or sideways. If you want to fly forward, you got to rotate nose down, and then you can accelerate vertically in the helicopter frame, but vertically in the helicopter frame will now be partially forward and partially up, and the up compensates for gravity, and the forward is what lets you fly forward. So you can build a model for this from collecting data from your helicopter, let's say, and learning a bunch of parameters that predict the next state given current state and action. Can we solve it at this point, the MDP? Actually, we need one more thing. We need a reward function that describes what we want the helicopter to do. For hover, we saw this. You can have a reward based on distance to target location, X star, Y star, Z star, and maybe penalizing for non-zero velocity, so you want it to hold still. Actually, we saw this example in the RL lecture of a helicopter reliably hovering, which is a very hard problem, but reliably solved through reinforcement learning, and in fact, reliably solved for flying upside down. Upside down is harder. How do you keep yourself upside down? Well, that main rotor can have a negative angle of attack, and that negative angle of attack, if you're flying the normal way, brings you lower, but if you're flying upside down, keeps you up in the air. And it's actually more efficient because when you pull in air, you accelerate it, and when you are flying normally, that accelerated air goes over the helicopter body, pulling it down, whereas if you're upside down, that accelerated air does not drag your helicopter body down. Now, what if you want to do something more complicated, though, like TikToks and so forth? What are you going to do? Or maybe you want to flip. In the video we watched, the helicopter had already been flipped. The pilot flipped the helicopter, toggled autonomous control for inverted flight, and that's what we saw in the video, autonomous control and inverted flight. We did not see autonomous flipping. Maybe you could say, well, let's write down a reward function by hand, because we get to choose what the helicopter should do. Let's just write down maybe a path the helicopter should follow. You think about, what should the helicopter do when flipping? Well, it should be spinning. But if we just pay attention to spinning, it's going to be dropping, so it should also stay in place. But staying in place is actually not possible, because when you are spinning and you're not able to generate directly vertical thrust, if you generate that vertical thrust in your helicopter frame, you'll move forward or backwards in some way. So you got to be a little careful about what you do there. So then maybe you watch a human fly and say, well, what I see them do is when they're horizontal, they kind of give a big push so the helicopter accelerates up, then they start a half flip, then it's falling down, they're inverted, they give it another push, accelerating it up, and do another half flip and repeat. So maybe we design as a target for this helicopter to do this kind of maneuver. But exactly what will be the details? It's not easy, right? Exactly how much do you push up? How fast do you spin? Difficult things to decide. A few years ago, as a PhD student, I tried to design this kind of thing. And so we designed a trajectory. This is me together with Adam Coates, Andrew, Morgan Quigley. And then had reinforcement learning, learn a controller to follow the trajectory that we designed. We ran many, many simulations, looking pretty good. And then we run it on our helicopter. So this is our helicopter, indeed flipping, which is great. It's moving more than we want it to move, a lot more than we want it to move. And it went into the trees. So let's think about what happened here. So in simulation, this all worked out perfectly. But in the real world, it turned out it didn't work. What happened in the real world is we're trying to follow this path that we designed where the maximal reward is, and it had learned a control policy that's in simulation really good at following this path. But in the real world, this path was not dynamically feasible because the helicopter cannot fly any path. Only some paths are possible. And so we had asked it to fly a path that's not flyable. So it starts deviating from that path. As it deviates from that path, what it learned in the simulator becomes less and less relevant to the real world. It learned to control around the path, but now it's on this different path. It doesn't know how to control around that path. It started overcompensating. That's why you saw it making these wild motions, overcompensating. It pushed the controls so hard that the engine died because it applied so much control, the engine just couldn't push it, died. At that moment, the blades stop spinning, or they slow down. You lose control over your helicopter, more or less at that point. Then what happened is our human pilot took back control to try to save the helicopter. And believe it or not, they actually saved this helicopter. Incredible. So the human pilot saw the engine died, took control. The blades were still spinning. As long as you have inertia in the blades, you have a little bit of control. Got the helicopter right side up with the power still left in the blades, the inertia left in the blades. Then got it into something called auto-rotation mode, which is where you use the airflow as you're falling, the airflow going through the blades to spin up the blades again. So you get new inertia in your blades. Then it went behind the trees. He couldn't see it anymore. But he knew from past experience he could predict. His dynamics model was pretty good, I guess, in 188 language. His dynamics model was just phenomenal. It's behind the trees. He doesn't see it. He knows kind of what's happening. And right before it lands, he changes the collective control to not absorb energy in the blades anymore, but to push it all back out. That kinetic energy that's in the spinning blades now goes into pushing air down to slow down the helicopter and have it land on its feet. It landed a little harder than you want to land, but it landed on its feet, and it could be recovered from that, which was pretty crazy. So clearly, human-level control at that point was much better than our autonomous controller. This is the same video. So we started looking at some human pilots. This is a picture of Alan Szabo, considered one of the world's best human pilots. He has a video out there called Sunday at the Lake. And Sunday at the Lake is a video where he's at this lake and he's flying a helicopter in ways that you could not imagine a helicopter could be flown, and it just works, unlike what you saw with our autonomous flight there. We said, well, clearly the issue was that we asked the helicopter to follow a path that's not flyable. So what if we collect paths from a human pilot and then ask the helicopter to fly those paths? But it turns out when we collect paths from a human pilot, they tend to be noisy. They don't do exactly what they wanted to do, and also our tracking of the helicopter is imperfect. So our recollection in the computer of those paths is still often not flyable paths. So we said, let's collect many demonstrations. So we collected many demonstrations, and for these many demonstrations, we figured that this set of demonstrations captures the essence of what it means that what we want the helicopter to do. but not any single one of them is precise enough or is exactly what we want, and just averaging them is not going to work either because they're timed differently and they're oriented differently, and averaging is not going to lead to a good path. So how do we from this get a specification of what we should be flying? Well, we could learn the trajectory from these as noisy observations. What methodology do we have for that? Hidden Markov models. If we have something we don't know that evolves over time, but we have some noisy measurements of it, we can run an HMM to recover what we actually want. So we want an HMM model that captures this. We have the hidden sequence of states, and we have multiple demos, typically 5 to 10, only 2 shown on the slides here. Now, one little catch here is that they're not timed the same. So you can't just hook them all up one by one and expect that this will work out, because they're in different phases of this air show. So what do? We use something called dynamic time warping. So what does that do? You can align 2 trajectories. So let's say you have many demonstrations, then you have a hidden trajectory which you just initialize with one of them. Then you run dynamic time warping, which aligns each trajectory with the hidden one, which was just a guess, but in the process also aligns all the demonstrations because they're all aligned with this one reference. After you do that, then you can run the inference in hidden Markov model, just standard BaseNet inference, which in this case is an extended Kalman filter / smoother, which is a forward-backward pass, similar to what we covered, but done for continuous variables rather than for discrete variables. You run that, you might get this out. But remember, our alignment was kind of noisy because we aligned over time based on some random initialization. So now that we have something a little better, let's actually realign each demo to what we found. Let's then re-infer through probabilistic inference what the hidden state might be. Keep repeating this till we reach some fixed point, and that will be our target for our helicopter to fly. What does this look like? Here is in white the target found through the hidden Markov model inference, and in color still the demonstrations. The demonstrations are now time-aligned because that's a side effect of running this inference. What you see here is something that's better than any single one of the demonstrations. I want to take a closer look. In black here is the inferred target trajectory, and in color are the others. The color ones are not that great, but the black one kind of summarizes the essence into something that we want. Okay, so now we're set. We have collected data to learn a dynamics model for the helicopter. We have collected data to collect the target trajectory. We can now penalize. Our reward would penalize for deviating from the target. And then we can run reinforcement learning in simulation, let's say, in this learn simulator to find a good controller and run it on the real helicopter. Now it turns out we need to do a little more than that. The controller we learn in simulation is still a little optimistic about really following that path. So while we fly the helicopter, we'll do depth-limited search to improve what we have. So as we're flying, we'll run a search over 40 time steps, the next 40 time steps, to see what is the best sequence of controls. And you might say, why only 40 steps? We control at 20 hertz. That's looking 2 seconds into the future. Really, you want to look further into the future. So what do? We have a value function. So really what we get from running reinforcement learning in simulation is a value function that evaluates how good each situation is at any given time. And we use that value function to be able to look ahead only 2 seconds rather than needing to look ahead much further. And that value function tells us, okay, how good is it to end up here? We also have reward at each time tick. And our search over those 2 seconds, capped off with the value function, is what results in the control we apply. So it's bringing together a bunch of different ideas, kind of single agent search, learning value functions, and learning models and reward functions through inference. Here's what we get. So fully autonomous, takeoff, flipping over during takeoff, hover. So this method can also learn to hover, no problem. Then it goes into forward flight, and it's going to do something called a split S, where you do a half roll, half loop. It's a way to change direction without burning all your energy to friction. A stall turn is a climb and then a 180 and come back down. Another way to change direction without burning your energy to friction. A loop I think the only use is to show off your control capabilities. You want to show it off more, you can pirouette around at the top. Stall turn, again, coming out tail first. Hurricanes are fast backward flying circles. The fastest we flew this helicopter was close to 55 miles per hour, so almost highway speeds. The helicopter's only this big, so it's pretty fast for something of this size. Inverted flight, we know how that works. Knife edge fall. And then now actually some of the hardest maneuvers. Why are these the hardest maneuvers to execute on? Stationary rolls and flips. Why is flying 55 miles an hour not harder than this? Well, when you do something like this, and here the tick-tock, the hardest maneuver in this air show, the reason this is so hard when you do things in place is that you're maneuvering an airflow you just generated yourself, which is very complicated airflow compared to when you fly 55 miles an hour. You're just going into new clean air, which is much easier to predict what's going to happen. And ending in inverted hover. So with this methodology, it was possible to fly these helicopters at the level of the best human pilots, assuming you had demonstrations from those pilots to kind of piggyback on to get to this behavior. Okay, that's for helicopters. Any questions about helicopters before we move to legged robots? Yes?
Would you have been able to do this without human experts?
So then, after this project at Berkeley, PhD student Woody Hoberg took charge on seeing how far we can get without human experts for some simpler things, not for all the maneuvers here. So what Woody did, he essentially set up the helicopter to learn from scratch. So he set it up on the ground, and it was supposed to reinforce and learn from scratch with a little bit of guidance. So a little bit of guidance meant that he would be there shutting it off if it started doing something weird. So essentially, he would shut it off whenever it starts tilting itself, so it lands on some pretty wide landing gear, so it's more stable. But that was the only human input required. He was able to have it learn to hover reliably, with the only human input being shut it off when it looks like it might start doing something dangerous. We did not push that further to flying those maneuvers. There is some work. I think that if you look at Woody was shutting things off. Then recently at OpenAI, there's been some work on robots learning to do backflips. And that was kind of one step further. It wasn't just shutting it off. You would watch a robot try things, and the human input would be not specifying a reward function, which is very hard to do for things like backflips, just like it was hard here. But what they did is they said, the human watches it and says which one is better or worse among a set of them. And then from that, it learns a reward function, which we'll look at here too in a moment. It learns a reward function and then optimizes against that reward function, does a few more. The human again says which one's better or worse, updates its learned reward function, goes again, and so gradually over time it acquires a reward function. And so the human input there was somehow guiding what reward function it learns. And we'll see some examples of that here too, but they did it for backflips. I think the other way to get minimal human input for the helicopter case is we put the helicopter very high in the sky where it has more time, and if it already has a recovery controller, then you could imagine that if first you learn a recovery controller with a little bit of human input, and then once you have a recovery controller, you just let it learn on its own and let it switch to recovery mode. And Claire Tomlin's group here at Berkeley has done some work in that direction, where they have a safe controller and a learn controller, and the learning controller is learning on its own while the safe controller keeps things in check so the helicopter doesn't crash. Yes?
I imagine like the helicopter runs out of fuel as you carry out an extended
Yes. Mm-hmm.
So like the maximum output would decrease, I suppose? Like, was that a problem?
Yeah, it happens to work the other way around. So it uses roughly a fixed amount of fuel anyway per time. So it's more that it has less weight to carry as it has used more fuel, so it actually has more power until the very end, of course, when it has no power left. The mass properties change a little bit. The fuel tank is pretty central, so it's close to the center of mass, so it's not like the inertia changes in weird ways. It just gets a little more power. Maybe a question related to that is, how much power does this thing actually have? This helicopter had, in inverted flight, where it has more power, 3 Gs. So we could generate 3 times the power of gravity. Of course, you need to generate one of them to even stay up in the air, but you still have 2 Gs left to do other things with. And regular flight had about 2.5 Gs maximum acceleration. Okay, let's take a short break here, and after the break, let's do legged locomotion and manipulation. All right, let's restart. Any questions about the first half? Yes?
Which method is used for the reinforcement learning in scenarios like these? Like, how are the helicopters being taught?
So the question is, which reinforcement learning method was used underneath what I showed here for the helicopter? So what we use there is a model-based reinforcement learning method. So we learned a dynamics model, so simulator, from data that was collected. We then, to learn a good controller in the simulator, we used something called iterative LQR. And iterative LQR, what it says it essentially looks at a trajectory and tries to find a linear feedback controller at each time slice. So the parameterization of the controller is a separate linear feedback controller for each time slice. And the way you learn that feedback controller for each time slice is by doing a forward pass to see what your current sequence of controllers achieves, and then you can do a backward pass, which is essentially a value iteration pass over that same trajectory to find the optimal sequence of feedback controllers. So it's essentially value iteration, but in a continuous space. In a continuous space, it's always harder to represent things, and so that's why we make a simplifying assumption. We assume that we are just going to use a sequence of linear controllers, and actually we approximate the dynamics with linear dynamics locally, because a lot of functions are locally linear, so as long as we're locally enough, linear can be fine. And we use a quadratic reward function. If you have a locally linear dynamics and quadratic reward function, it turns out that's the one continuous state action space scenario where you can run exact value iteration, even though everything's continuous. And it gives you a sequence of linear feedback controllers. And then we repeat. We run that sequence of linear feedback controllers, and that will follow a new path. Along that new path, we linearize the dynamics, because the dynamics is not really linear. We approximate it linearly. We do another backward pass along that and keep repeating this till it's converged. Once we've done that, we have value functions everywhere, and we have linear feedback controllers everywhere. If there's no wind, you can actually just run the linear feedback controllers, it'll be fine. But if there's some wind gusts that could throw you off, you then want to, instead of using the linear feedback controllers, you want to use the value functions and the 2-second look ahead against those value functions to do the controls.
Something like feature-based fueling is possible.
Something like, training a unified policy across the entire space might work. At the time, that was not something that we did this experiment in 2008. At that time, that was not something that anybody got to work on anything. So definitely not on such a hard problem. It could be interesting to revisit that now and see what the current understanding of how to train these networks, can it be done with one unified network? Likely it can. Might take some work exactly figuring out how to do it. Okay, legged locomotion. Maybe a little bit of perspective. When you think about robotics, it's often easy to think about also what humans do. So you think about what humans do, you might say like, okay, we can run, we can grab stuff, but we cannot fly. And so you might think, okay, well, flying must be the hardest because we can't even do it. But the truth is that while flying is hard, and definitely helicopter control is not an easy problem, it's in some sense easier than walking. And the reason it's easier is because if you're flying, you're up in the air, everything is the same. The air here, the air there, unless there's some weird airflows, that's the only thing that really changes. Whereas when you're walking, the surface could change all the time. You need to react to that, understand what's happening there. A lot more change in your environment. And so walking tends to be harder than flying for robotic control. Here's an example of how hard this can be. This is a video from 2015. 2015, there was the DARPA Robotics Challenge, which was held in Pomona, just east of Los Angeles. People had 2 years to work on this. And what did the robot have to do? It had to essentially drive a car or walk, but driving the car was recommended, then get out of the car, walk a little bit, open a door, grab a drill a hole, walk some more, and that was essentially it. So doesn't sound that complicated, but actually, it turned out very complex to get a robot to do that. And here's some footage from the competition. And keep in mind, these are people who those worked on for 2 years, typically. And it's indicative of how hard it is to do walking with robots. So a lot of falling here, and you might wonder why is all this falling happening, even on flat surface. Often the robot is thinking it's going to grab something, but then it doesn't grab it, and it's generating a force to pull it or rotate it, but there's no counterforce. And so it did not sense correctly what is going on in the world, and so did not react correctly to the world. Now, I was there for the competition, and it's very funny to watch the video, but it turns out at the competition, everybody was really sad for the robots when a robot fell. Nobody was laughing. I was like, oh no, poor robot. Very different. It was very interesting to see how people really connected with these robots and really felt for them and wanted them to succeed. Now, this is indicative of how hard this can be, and why is this so hard? Like, why did this not just work? Well, if you look underneath of a lot of what was going on in these approaches was they would build a model of the world. They would have sensors. Those sensors would suppose to build a model of the world. Based on that model, you could simulate the world, predict what you should do. Not unlike what we did with the helicopter. We learned models of how helicopter dynamics works. Think about what will happen as a function of which actions we take and maybe have a value function, and then take the actions that lead to the good outcome. Thing is, modeling these situations proved even harder than modeling helicopters because your sensing needs to understand whether or not you're already making contact. And making contact or not, you could be very close but not have contact. It's a very subtle thing. You don't have contact, you don't get to apply any forces, don't get any forces back. So it's very hard to do this. Now, what's changed recently, in the past few years, is that through advances in deep learning, it's been possible to better map from raw sensory information to controls you might want to apply. And so actually, you've seen this video before. This is from a little later that same year. It's in simulation, but this robot is over time learning to control itself to do walking. And ultimately, it learns to walk. Now, of course, never believe it's as convincing when it's in simulation than when it's in the real world, so it's definitely always harder in the real world. But what you see here is a direction that enables for the system to just learn on its own, to go from sensory inputs. In this case, the sensory inputs are just joint angles, joint velocities, coordinates of center of mass, but to go from those measurements to controlling the robot reliably. And the beauty, of course, with reinforcement learning, which is behind this, rather than a more model-based approach as we saw in the videos, the reinforcement learning algorithm can be reused directly onto other robots and can learn to control these other robots. Now, with this in mind, of course, if you look at the amount of data collected, that's still a little tricky. It takes a good amount of data collection before this robot has learned. If it's a physical robot you're trying to train, it gets tricky because you might break it before it has learned enough. And even if it doesn't break, it could take just unmanageably long to get the amount of data you need. But it shows in simulation, at least, a lot of progress towards learning intelligent locomotion behaviors. Here the reward function is the closer your head is to standing head height, the better. So sitting is better than lying on the ground, and standing is even better. So how about other motions? At this point, it is possible you run enough simulation to train up a very wide range of skills. So this is a result from Jason Peng, PhD student here at Berkeley. And at this point, if you have a motion you want a robot to master, Jason's methodology can pretty much make it happen. So this can work directly for building video games. You build video games, you want your main character to move in a realistic way. You can have it sequence together motions like these and dynamically simulate how they interact with the world rather than keyframe every little detail. Same for animated movies. Now, how about real robots? Let's say you want to get this robot across this terrain. Well, if you think about it, there's really two problems here. You could think of it naively just as low-level control and applying torques at the motors, but then it's a very long problem that doesn't have, and when you solve it that way, you don't have much perspective over what you're trying to do. It could make more sense to think of it as, well, I want to find a path across these rocks, and once I find a good path, I want to control the robot to follow that path. So there's a low-level control, which is about placing your feet in the right next position, and there's a high-level control problem of what's a good path to follow. High-level control problem, that's actually A-star search. If you have a cost function for this terrain, and what would the cost function be? Well, what could it be? Where do you want to be? Where do you want to place your feet? Well, you maybe don't want to be next to a big cliff, because if you're right next to it, then you slip a little bit, you'll slide your foot down, and that's not good. Maybe you don't want your feet at very different heights, because then you're tilted. It might be less stable. Maybe you look at the 3 feet on the ground and the fourth one that's moving, the 3 on the ground, the support triangle of that. If you project down the center of mass of the robot, should maybe fall within that support triangle, because then it won't fall over. So there's a bunch of considerations you might have. When we thought about this problem, we had 25 features we came up with that we thought matter for the reward function or the cost function when you run the search or the value iteration, which is more or less equivalent, to find the path across this terrain. But if you choose the trade-off between the features differently, you'll find different paths. So how do we set that trade-off? We tried by hand. Say maybe a little more weight on support triangle margin, maybe a little more weight on height difference, and so forth. Very hard to do. Instead, what you can do is you can actually learn the weights in the features. So reward learning. How do you do reward learning? You demonstrate a path across this terrain. Demonstrating doesn't mean just drawing a line. It actually means choosing a sequence of footsteps that it executes on, and assuming it does well. This assumes you have a low-level controller, but that's well understood how to do that. That's low-level control can be done by just running search in a relatively small space. So you choose the next footstep, next footstep, next footstep. Then you learn a reward function that is such that if you were to run value iteration, or if you call it a cost function, if you were to run A* search, that the path you demonstrated is the result of running value iteration or A* search. Okay? If you can find that reward function is a good explanation of what you want this robot to do, including in new situations, new terrains, where it can then also calculate the reward on new terrains. We use that reward function on a new terrain, and then plan on that new terrain with that reward function, and let's see how well it works. So here what we'll watch first is without reward learning. So we said everything is equal reward. It's just about making progress, just as if you're on flat terrain. So it's going to kind of steadily march forward. Let's see what happens. So pretty good so far, but now it's on the rocky terrain, and one of its feet slipped down, another one is slipping down, one foot got stuck between the rocks. The low-level planner is trying to find a way out to make that foot go to the next spot, but that doesn't work. So it just had a bad choice of footsteps, which led to this result. What if we use the learned reward function? The reward function that, if used on terrains where we demonstrated, would result in our demonstrated paths. Well, let's take a look. With reward learning, robot in action. The feet will still slip, but they're placed cleverly such that a little bit of slippage does not result in the robot getting stuck and actually gets across very quickly. Any questions about leg locomotion before we go to autonomous driving? Okay, let's switch to driving. So, kind of the big push, recent push in autonomous driving started around 2005. So in 2005, DARPA organized a competition. In that competition, you're supposed to have your autonomous car drive a desert race. It's a time trial type race. There's no other cars you have to overtake, but you're kind of on your own and try to do it as fast as possible. 150 miles off-road. This is what the road, well, it's on a road, but it's this kind of road that is not like a regular road, so it's pretty hard to distinguish road from non-road, and if you steer off the road, you might kind of lose your car if you go down some kind of ravine or something. So a bunch of teams participated. In fact, there was a race the year before where nobody got more than 3 miles or something. But then they did a second iteration of the race, hoping somebody might get further with their car than just 3 miles. Now, this video actually has sound, and I'm not sure if sound works here. Not hearing anything. Let's see if this can be made to come out. Sound, headphone. Should work. Not hearing anything. Maybe let's try something different. What is the sound?
First time it's ever been done. Autonomous vehicles.
Does this work?
As dawn breaks over the desert, robots prepare to boldly go where no robot has ever gone before.
And we have movement from Stanley, ladies and gentlemen, the start of the DARPA Grand Challenge.
After months of tireless effort, there's a lot at stake.
And now Sandstorm.
A vision they all share will now be put to the test.
Launching of the sixth block here. Yeah. Are we there yet?
Each one leaves the chute with confidence. A far cry from the first Grand Challenge, when many faltered within sight of the start, and no robot went beyond 7 miles. During the first 8 miles of the race, Highlander gains 2 minutes on Stanley.
It's the rival school.
Behind Stanley, Sandstorm is closing the gap and may pass the Stanford robot. At mile 26, Team Dad's laser comes unbolted from the roof. Behind it, Stanley is rapidly approaching.
So the front car is the autonomous car. The one behind it is a follow car with human drivers that can stop the front car just in case something goes wrong. At that point, you're out of the race though. Once you're stopped, that's it. So you don't want to have to press that stop.
After leaving the starting line, Stanley now leads the pack, and just 5 robots remain on the course. To finish, they must wind through a treacherous mountain pass and stand. appears in the distance. After driving 6 hours and 53 minutes at an average speed of 19 miles an hour, Stanley is about to become the first vehicle in history to drive 132 miles by itself.
So that was 2005. Not everything went so well. There was other participants doing other things. Here's a bit of the blooper reel. This was a really hard problem at the time to get this to work, and it was very impressive that, in fact, four cars finished the 150 miles. That's the Berkeley entry. Only motorcycle in the race. Yeah, you will now take a seat in the autonomous cars of 2005. Now, what goes onto those cars? There's a few different things. There is IMU, like we're on a helicopter, a lot of computers, a GPS compass. If you have multiple GPS and they're very precise, you can know which way you're facing. Regular GPS to get position, e-stop, lasers, where you shoot out laser beams, and based on how long it takes for them to get back, you know how far away the nearest obstacle is in that direction, assuming it's an obstacle that reflects back to where the laser came from. Cameras, radar, control screen, steering motor. Steering control, usually you would have a high-level planner choosing a path, and then a low-level controller that is good at following that path. How do you decide what path to follow? Often your sensor readings will tell you if there might be obstacles or not. So your laser would see how far away things are. Now here there is an obstacle. It would see that the readings are different and decide it needs to steer around it, hopefully. If you're in an urban environment, there will be a lot more obstacles. A lot of readings will be noisy. And so it's typical to run something like an HMM to denoise those readings into a more reliable GPS, IMU, and laser readings into a more reliable estimate of the geometry of the world around you. So raw measurements might give you 12% false positives. With HMM, you get 0.02% false positives of where there might be obstacles. Cameras are important too, of course. With a camera, you can often look further ahead. So you might wonder, why do we need cameras if we already have LiDAR? LiDAR sends out a laser beam, measures how long it takes to get back. But usually it doesn't work beyond 50 meters. You don't get enough signal back. Also, sometimes if you have a very dark object, it might not reflect back. Or if you have a mirror, it'll reflect back in a way that doesn't come back to you. So, many reasons to still want cameras. Here it's specifically about looking further. You want to look far ahead. A camera will be better at that than a LiDAR. Okay, now how do you avoid running up a tree if you use your cameras? Well, you need labels. Somebody needs to tell you what was road, what was not road. Well, the way you could build vision for a car, because labeling is expensive, you could decide that you drive your car, and wherever you ended up, the LiDAR can tell you what is road, not road, because it's nearby, and you can, after the fact, backtrace what it looked like 2 seconds before that, 5 seconds before that, in your video stream, what that point looked like, and then automatically label it as road or not road, and that way your camera system can be trained to look further ahead. It's called self-supervision. And self-supervision is a trick that's very widely used to reduce labeling efforts. So the camera now knows all the red here is road. In urban environments, there's even more you need to recognize, not just road versus not road. A lot of progress has been made. This is a video from 2013. So after 2005, 2005 was a desert race where Stanley won. 2006-07 was Urban Challenge. After that, secretly, Google started a project on self-driving cars with many people from the winning teams. That project that came out a few years later, and here's a video from 2013, the Google self-driving car project. The encoding is a little messed up at the very beginning, but this is a video from the viewpoint of the driver, but it's an autonomous driver here, of the Google car in 2013. So very impressive. Can already do a lot of things. This is only getting better. This was before deep neural networks were like heavily used for this kind of thing. It's only getting better to recognize what's in scenes thanks to deep neural networks. Instead of classifying into which category is in the image, you would classify each pixel as to what's in each pixel. That way you get a semantic segmentation of what's in front of your car. Now, that video was from 2013, already very impressive. Didn't use any of this as far as I know. Definitely not the latest advances in this. So what does it tell us? Well, the devil's really in the details in the long tail of special events that can happen when you're driving. In fact, when you're driving, typically you wouldn't get in an accident, but periodically you get in an accident, or some humans get into accidents, and it's because something very special might happen, unexpected, a lapse of attention, or something really weird, and all of a sudden you don't react quickly enough. Same for self-driving cars. You can measure progress by just demo videos, which is one way, and it gives you some kind of feel for what's going on, but the 2013 video is already very impressive. So another way to measure progress is to see how are these cars doing relative to human drivers. So left and right are the same plots, but the right is on a log scale, so you can see more detail. It's a number of events per 1,000 miles driven. 10 to the negative 5 events per 1,000 miles driven for humans. Red there is human fatalities. So 1 in 100,000 times when a human drives 1,000 miles, they get into a deadly accident. Then yellow is human injuries, which is about 10 to the negative 3 per 1,000 miles. Then human crashes, which is between 10 to the negative 2 and 10 to the negative 3 per 1,000 miles of human driving. And then in green is the Google/Waymo disengagement. It's when the driver decides they want to take control because they don't trust the autonomous system right now to avoid an accident. And we see that it's going down how often that needs to happen, but still a bit removed from where humans are at. Where does this data come from? If you test in California, you have to report this data to the DMV. Google's not the only one doing this. Early on, they were the only ones as far as I know, but there's more companies now, and you can look at them on these plots and see which companies are how far along in terms of how many disengagements they need per 1,000 miles driven. Still, so far, quite removed from human accident rate levels. Another thing people have been pushing as a consequence of all this is lower power neural networks. So, for example, Kurt Koitzer at Berkeley has projects on this called SqueezeNet, where you say, when I have neural nets, I need to make so many decisions. If they're gigantic, use a lot of power, that's a problem. Let's see what we can do to build smaller networks to make decisions. What else did we not cover yet? Personal robotics. I want to spend a little more than 2 minutes on that, so let's keep that for Thursday. That's it for today. Bye.